An incorrectly installed timing belt or timing chain is one of the most critical mistakes that can occur during engine service. These components synchronize the crankshaft and camshaft rotation so that the engine's valves open and close at precisely the right time relative to piston position. This synchronization governs air intake, exhaust evacuation, combustion efficiency, and ultimately engine performance. When the timing belt or chain is installed incorrectly, even off by a single tooth, the entire combustion process becomes unsynchronized. The effects can range from rough idle and poor acceleration to catastrophic engine failure such as bent valves or piston damage, especially in interference-type engines where piston valve clearance is minimal. Proper valve timing is therefore foundational to efficient combustion, smooth engine operation, emissions compliance, and long-term mechanical longevity. A timing belt, typically made of reinforced rubber with Kevlar or fiber cords, contrasts with a timing chain, which is composed of hardened steel links. Belts are quieter, but have scheduled replacement intervals usually between 60,000 and 100,000 miles, while chains are marketed as lifetime components, but are still subject to wear in tensioners and guides. A belt often fails by tooth skipping or breakage, whereas a chain's issues arise from stretching or improper tensioner function. Both rely on precise alignment marks on the camshaft, crankshaft, and in some cases, intermediate shafts. A deviation of even one tooth, roughly 5 to 10 degrees of crankshaft rotation, can cause noticeable drivability and mechanical symptoms. The observable symptoms of an incorrectly installed timing system can be grouped into several categories: mechanical, performance, combustion, electronic, sensory, and catastrophic. Mechanically, the engine may exhibit unusual knocking, tapping, or loss of compression, and in severe cases may not start at all. From a performance standpoint, the vehicle can suffer rough idling, poor acceleration, hesitation, or loss of power. Combustion-related issues include misfires, backfiring, or running rich or lean. The electronic system may display diagnostic trouble codes such as P116 through P119, which indicate crankshaft to camshaft correlation errors, P0300 for random misfire, or P171 and P172 for fuel trim irregularities. Sensory cues include whining, rattling, exhaust popping or vibration, and at the catastrophic end, bent valves or piston valve interference can occur, leading to total loss of compression. Each of these symptoms carries its own severity, ranging from mild drivability issues to complete engine failure. When examining each symptom in detail, several patterns emerge. A hard starting or no start condition occurs because the crankshaft and camshaft are out of phase. The engine control unit cannot achieve proper ignition timing or valve overlap. The result is insufficient compression to ignite the air-fuel mixture. This is a severe condition where the engine may crank but never fire. Rough idle or stalling occurs when incorrect valve overlap causes unstable combustion at low RPM. Idle air control and fuel trim systems constantly compensate for the unstable airflow, leading to fluctuating idle speed or engine stalls. This is often accompanied by random misfire codes such as P0300, and scan data will show short-term fuel trims oscillating widely. A loss of power or poor acceleration stems from retarded valve timing, which delays the intake and exhaust events, reducing volumetric efficiency. The throttle response becomes sluggish, especially under load, and the issue's severity depends on the number of teeth the timing is off. Backfiring through the intake or exhaust results from valves opening or closing at the wrong time. Early valve opening allows ignition of the mixture while a valve remains partially open, creating sharp popping sounds through either the intake manifold or tailpipe. Engine misfires accompanied by a check engine light and codes P116 through P119 indicate that the ECU has detected a discrepancy between camshaft and crankshaft sensor signals. This correlation error often accompanies a misinstalled belt or chain. Persistent misfires not only degrade performance, but also risk damaging the catalytic converter due to unburned fuel. Mechanical noise also offers strong clues. On a belt-driven system, slapping, chirping, or whining suggests a misaligned belt or tensioner, while on a chain-driven engine, rattling or clattering noises, especially on startup, indicate improper chain tension or preload. These noises can precede catastrophic failure. Low compression readings on all cylinders confirm that valves are not closing fully during compression strokes. A compression test that shows uniformly low readings across multiple cylinders points to significant timing deviation, whereas uneven compression suggests localized mechanical damage such as bent valves. Fuel and emissions irregularities arise because the ECU attempts to compensate for poor combustion by altering injector pulse width and ignition timing, producing rich or lean mixture codes and stressing the catalytic converter. Fuel economy declines as a result. Accurate diagnosis begins with a combination of electronic and mechanical checks. The first step is to use an OBD-II scanner or professional diagnostic tool to look for codes, crank to cam correlation errors, P116, P119, camshaft sensor faults, P40, P341, and misfires, P0300, P30X are common. Live data should then be reviewed, comparing the actual versus desired camshaft position. A variance of more than 5 degrees generally indicates a timing offset or chain stretch. A physical timing mark inspection is also critical. With the crankshaft rotated to top dead center on cylinder 1, the technician verifies that the camshaft alignment marks match the manufacturer's specification. A misalignment of even one tooth is often visible when cam gear marks are displaced by several millimeters. Compression or leak-down testing follows. If compression is uniformly low, the issue is likely valve timing. If one or two cylinders show low compression, mechanical damage such as bent valves may be present. Advanced diagnostics using an oscilloscope can capture crankshaft and camshaft sensor waveforms to compare phase relationships without disassembling the engine. A deviation in phase angle on the scope confirms timing error. Physical inspection of the system itself remains essential. For belts, check tensioner preload, idler alignment, and tooth engagement. For chains, inspect for tensioner extension that indicates chain stretch, as well as wear on guides and VVT sprocket phasing marks. Once the problem is identified, correction requires retiming the engine. The crankshaft must be set to true top dead center on the compression stroke, and all camshaft and balance shaft marks aligned precisely according to the manufacturer's diagrams. The belt or chain should then be reinstalled with proper tension and preload. After reassembly, all diagnostic trouble codes should be cleared and learned cam-crank values reset if the ECM allows it. Before attempting to start the engine, rotate the crankshaft by hand through 2 complete revolutions to ensure no piston-valve interference and confirm the timing marks realign exactly. To prevent errors during installation, always reference OEM repair manuals for correct mark orientation, torque sequences, and tensioner adjustment procedures. Replace worn tensioners, guides, and seals during any timing service, and use manufacturer-specific locking or alignment tools, such as Ford cam holding tools or Volkswagen TDC pins. Never rotate the camshaft or crankshaft independently once the timing belt or chain is removed, as this immediately risks losing synchronization. Real-world examples demonstrate how these principles apply. On a 2008 Honda Civic with a 1.8-liter timing belt engine, symptoms included rough idle, poor acceleration, and a P116 diagnostic code. Inspection revealed that the timing belt had been installed one tooth retarded on the intake camshaft. After realigning the belt and verifying correct tension, idle quality and performance were fully restored with no valve damage. In another example, a 2013 BMW 328e equipped with the N20 turbocharged engine and a timing chain presented with a rattling noise at startup, a P117 code, and loss of low-end torque. The issue traced back to incorrect chain tensioner preload after a previous service, which allowed chain slack and phase error. Retiming the engine using BMW's camshaft locking fixtures and replacing the tensioner restored proper operation and eliminated the correlation fault. The long-term risks of operating an engine with incorrect timing are substantial. In interference engines, piston contact with open valves can bend valve stems or crack guides. Unburned fuel caused by repeated misfires overheats and destroys the catalytic converter substrate. Continuous detonation or pre-ignition due to wrong combustion phasing stresses bearings and connecting rods. Furthermore, improper tensioning accelerates belt or chain wear, leading to premature failure of the timing components themselves. Certain engine designs are more vulnerable than others. Interference engines are a type of internal combustion engine in which the paths of the pistons and valves overlap within the cylinder, meaning that if the valve timing becomes incorrect, such as from a broken or misaligned timing belt or chain, the pistons can physically strike the open valves. This design allows for higher compression ratios, improved efficiency, and greater power output, because the valves can open farther into the combustion chamber, but it also makes precise timing absolutely critical. In an interference engine, even a small timing error can destroy the engine. Non-interference engines, such as some older Ford and Chrysler designs, avoid catastrophic damage but still suffer from poor performance and efficiency when mistimed. Several key insights summarize the diagnostic and preventive priorities. Even a one-tooth misalignment can create significant drivability issues, so mechanical and electronic timing correlation must always be verified. Trouble codes, P116 through P119, are the primary electronic indicators of such misalignment. Low compression readings or persistent misfires should always raise suspicion of mechanical timing error. In interference engines, never attempt to start the engine if alignment is uncertain. Rotating by hand first can prevent catastrophic piston-valve contact. Proper tensioner preload is essential, since incorrect tension can mimic or cause timing offset symptoms. Finally, always rotate the engine manually through 2 full revolutions after timing installation before initial startup. For practical documentation or repair records, it can be helpful to note variables such as the vehicle make and model, engine type or size, whether it uses a belt or chain, the specific symptoms observed, and the diagnostic tools available. This context allows targeted application of the procedures outlined above. In essence, an incorrectly installed timing belt or chain may appear as a range of issues: rough idle, misfire codes, loss of power, or backfiring, but they all share a single cause: mechanical missynchronization of valve and piston motion. The most accurate diagnosis combines physical inspection of timing marks and tensioner setup with electronic confirmation through OBD-II data. Prompt correction prevents extensive mechanical and emissions-related damage, ensuring the engine once again operates with the precision its design demands.